Power laws and preferential attachment model calibration. Interesting.
Okay, let's see. I'm supposed to tell you about this, MURI. It stands for Multi-University Research Initiative. This is an Army grant that involves 5 universities. So we're in the 4th year, and it's multidisciplinary, so we've actually been talking to computer scientists and electrical engineers. It's amazing. You'll see the influence as I go along. So this model that I'll talk about, when it was first introduced to me, it was called the Krapivsky model, which was earlier work, and then it was generalized by some of our distinguished colleagues. And it goes like this. So when I understood this was about dynamic networks, I understood dynamic means the network was growing, and this topic seemed appropriate. So this is a model which has a fairly small number of parameters, which is good and bad. So there's 5 parameters, but really 4, because 3 of the 5 add up to 1. All right, so it's fairly simple. There's what you might call scenarios. So there's 3 of them, and imagine flipping a 3-sided coin. So there's going to be 3 parameters for the coin, alpha, beta, gamma, which add up to 1. And then there's 2 extra parameters, delta in and delta out. And I understood from my computer science colleagues that they added these parameters later when these models became popular, because they saw that without them, the deltas, when they saw without them the data didn't fit the model very well. So there's going to be a growing directed graph indexed by n, and this directed graph is got n edges but a random number of nodes, but the random number turns out to be a binomial number, so it isn't a big deal. But the n is indexing the number of edges. And the set of nodes will be v sub n, and the set of edges will be e sub n, and I would appreciate it if you don't ask me why some things are subscripted and some things have parentheses. Some things are lost in the mists of history. That's the truth. All right. Now the nodes come with in degrees and out degrees, and the in degrees are referenced with the graph that you're doing the counting in. So I've put the superscript n to remind you, but this isn't going to be a big deal. And you construct these graphs kind of recursively. Once you know gn minus 1, there's a prescription for how you're going to get gn. And here's the prescription. There are these 3 scenarios, and they happen with probability alpha, gamma, and beta. And I'm aware that in the Greek alphabet, before George starts vibrating in indignation, I'm aware that gamma is not the letter that follows alpha, but there's a reason for doing it this way. So with probability alpha, a new node, v, comes along and attaches itself to an existing node, w. How does it choose the w? It chooses w with a probability that depends on the in degree of w, and then the probability is perturbed by that delta. And the denominator is just designed to make it so that when you sum over the possible w's, you get 1. Second case is the new node comes along, but the attachment goes in the other direction, so we're constructing obviously a directed graph here. These edges have directions. So with probability gamma, the new node gets attached to by an existing node w. How do you choose the w that's going to do the attaching? Again, it's according to the out degree of w, and it's modified by the delta sub out. And then the third scenario is happens with probability beta. You don't create a new node, you simply create a new edge. You pick 2 nodes at random, independently, and If the two nodes are V and W, the arrow will go out of V according to the out degree of V, and it will come into W according to the in degree of W. So that's the rules for preferential attachment. Okay? So 5 parameters, but really 4. Good? Yeah?
In the third scenario above, you choose, with probability beta, you choose V and W at random, and then or you're doing this for, essentially, you're doing this for every pair with probability.
If you wind up with V and W, it happens with that probability, and it's as if you chose V and W independently. That help? Okay, so here's what's known. So n parentheses n, number of nodes. It's going to be a binomial random variable because it's affected by the beta in there, where you're not adding a node. And then so the process is indexed by n, which is the number of edges. And n sub ij is the number of nodes with in degree I, out degree j in the nth graph. Okay? So nowadays we would think of this as in a martingale way, but however you do it, you look at the empirical frequency of nodes which have in degree I and out degree j, and that will converge to a limit pij. So I've taken a limit on n. All right? There's going to be another limit, and here it comes. Now this pij, what was known was marginally it had a power law. So pij is the asymptotic probability of having in degree I and out degree j. If you marginalize this by summing over the j's, you get a power law in I, and if you marginalize by summing over I, you get a power law in j. And in general, depending on those 5 parameters which we use to build the model, in general, those two indices are different. And we would have loved to call them alphas, but we already used alpha, so now it's the Greek letter iota. Among the 4 people on this project, I was the only one who knew what letter that was. And it wasn't because of my classical Greek education, I can assure you. Anyway, so marginal power laws. And these indices that we get for the power laws, the iota in and iota out, they're 1 plus something. Don't worry about the specific form of it. I don't think the human brain is wired to remember these formulas. But they're 1 plus something. Now, we're going to create a fictional pair, I and O, for in and out. And remember this limiting frequency, Pij. So imagine that I-O has mass function Pij. So what we've just stated is that the distribution of I has a power law with index iota in, and the O, corresponding to the out degree, has a power law with index iota out. If you translate this into tail probabilities, then of course the indices reduce by 1. So you get iota in minus 1 for the tail probability and iota out minus 1. And that would be the way the probability community would write this, but most people find this more compelling where you deal with the mass function directly. Now there's something called multivariate regular variation or multivariate power laws, and the question is, does this have that property? The answer is yes, but since the indices of the 2 marginals are different, it's what's called non-standard regular variation, which isn't a huge deal, but for something that intellectually is supposed to be simple, making the transformation, it's kind of a nuisance, and it creates some problems with the estimation. Okay, so marginally that's the story, and now we're going to go into the multivariate case. Now, let me tell you first of all, or let me remind you, remind is in quotes. I always say that to the undergraduates. These are things you should have learned in high school had you been paying attention. But this is not as well known. So the multivariate regular variation, what does it mean? So you have a random vector. You can do this in any dimension. You can actually do it in a metric space if you're feeling exotic. It has, in this case, we have components x and y. It has non-standard regular varying tails if there exist two scaling functions, a and b. And what do? You take your vector, you scale x by a, you scale y by something different, possibly b. Now you have a new vector, you look at its distribution, you multiply by t, you let t go to infinity, and out at asymptopia has to be a nice friendly measure waiting for you. All right? So it's going to converge to a limiting measure. That's regular variation. It may not look like what you're used to with power laws, but you can write the definition of a power law so that it looks like this in one dimension. And to get the appropriate generalization, this is how you formulate it. The scaling functions a and b turn out to be one-dimensional regularly varying functions, and we'll always assume indices are positive so that there's no funny business going on. All right, so that is regular variation. What did it have to do with the mass function? So far, nothing. Yes?
Why do you need x and y to be positive? It's written random vector x and y positive.
Why do I need it?
Yeah.
That's a good question. You need x and y in a cone, and then this would work. But x and y on the next slide become I and O one more time. You know, they become the I and the O, and those are positive. It's just more convenient to do it in this, so you don't have to talk about the range and all that. So it's mostly convenience, but you're right. Yeah, I don't need it. Yes. Okay, so now there's a little story about this arrow, which I'm mostly going to skip. So what does the arrow mean? You know, it's like weak convergence. What does weak convergence mean? It's convergence and distribution. But that's really for another day. I'd love if you don't make me get into this. Nice sets you can put in there. So in this dot, you could put in a nice set, whatever nice means. That's enough for what we need today. The traditional way of doing this would be vague convergence. There's something else called M convergence, which was started by Holt and Lindskog, and I got involved in a project where I felt this was really important and nicely rounded out the theory. So it's, I think, in a good state. My Stockholm colleagues in the audience, please say hello to Holt and Lindskog if you see them.
So I don't want you to expand long on that. If you have an answer in one sentence, is M convergence more general than vague convergence?
Vague convergence generally requires a compactification. And then once you compactify, you have to uncompactify by removing something. And this M convergence is more flexible because you start with something removed from the state space. It doesn't have to be one point the way the vague convergence formulation requires. You're going to let me get away with that?
Yes.
Good, thank you. It's a friendly audience. This is good. All right. The joint regular variation that I've just defined, it implies marginal regular variation. This looks at least a little more like a power law. And in the case today, I called this non-standard regular variation. It's non-standard because the indices here may not be the same. In the standard case, they are the same. In the standard case, in fact, the scaling functions can be the same. And then everything scales, and you get kind of self-similarity parameters coming in. But that's not the case here because these powers can be different. So now we're going to think of the x and y as the I and the O, the things with the limiting Pij. Okay? Now we're going to look at the joint distribution here, and there's two ways to proceed. First of all, I call it the full frontal assault. You just go at this directly. And an alternate to the full frontal method is the transform method. We developed this multivariate Tauberian theorem, which we're going to use generating functions to analyze this, which people will not be surprised in because difference equations come in. But with generating functions, you're a hop, step, and a skip away from Laplace transforms, and then it makes sense to think in terms of Tauberian theory. So we developed in parallel the Tauberian theory, and then we discovered we really didn't need it because we could do it directly. So I'm going to skip the Tauberian theory today.
Wait, so I would have thought that this is sort of almost like a method of moments, not quite generating functions. So you would have thought that generating functions is more elegant and easier, and then you wouldn't want to do the just brute force frontal assault anymore. But you're saying it's the opposite, the frontal assault is actually easier and more
The
elegant?
brute force frontal assault uses generating functions.
I see. Okay.
All right, now, so the first method is just go at it. Take your hammer out, whack away. And then the second method is, well, we're kind of interested in the mass function itself, not the distribution of the random vector I/O. So we're going to attack the mass function directly, and then there are a few surprises when you do that. But I'll get to that in a minute, at least on a very high level. All right. So what do you do here? Now this construction to go from Gn minus 1 to Gn was kind of Markovian, so it's natural to think in terms of difference equations, and the PIJs, these limiting frequency probabilities, they're going to have a difference equation representation. And once you've got a difference equation for the PIJs, you would think of solving it by taking generating functions, and then you get a partial differential equation for the generating function. So phi is going to be take your PIJs and transform an I with an X, transform an J with a Y, sum it all up, and when you solve the PDE, if you don't make any mistakes, this is what you get. And I'll tell you what the phi1 and the phi2 are, but again, these tend to be a little bit complicated, and you don't have to remember it. But what you should notice here is that, first of all, there's a mixture, and I'm multiplying the first generating function by x and the second generating function by y. Now, what happens when you see an x in front of a generating function? You think that you had a random variable 1 plus something, and the 1 comes out as the x. Similarly with the y, it's going to be 1 plus whatever corresponds to the j. So you're going to see 1s in a minute, and that's where it's coming from, these x's and y's. So this is, I mean, what I don't like about this is it's a little bit fragile. If I change the assumptions, then I got to do this analysis all over again. I would like something a little more robust, but it's direct and seems to be something that works. All right. Now, remember there was this kind of mixture, and then there's a phi1 and phi2. And you take out your iPhones and click those formulas. Never mind, I'm just joking. Phi1 and phi2, and that's what they are. Now you initially look at them, and you say, there's no hope. What are we going to do with that mess? But then you stand back about 500 feet, and you think, well, maybe this isn't as hopeless as I thought. So what do we got here? We have a negative power of z dz. What does a negative power of z make you think of? It's a Pareto density. Ooh, maybe this is okay. And then we get something to a negative power, and it's x, remember, was between 0 and 1, plus 1 minus x times the z. That's going to be a negative binomial generating function, which you may or may not remember. The problem is it's, what is negative binomial? The number of trials until the rth success. So it sounds like you need an integer, but the negative binomial, we don't have an integer, or not necessarily at least. And the negative binomial is infinitely divisible. You never thought you'd love infinite divisibility, right? But there it is. It's infinitely divisible. Similarly, another generating function which looks like that. So maybe we got a shot at this. Now, there's two constants, C1 and C2, and they're transforms of the tail indices. So, you then think, well, maybe this isn't hopeless. You go and analyze the phi1 and the phi2, and here's the answer. I'll come back and talk about how you get the answer. So we do get joint regular variation. Remember, I and O were the fictitious random variables that I manufactured, which had the mass function Pij, the limiting empirical frequency. And you normalize by, this is actually C1, but you normalize by a power of t. You normalize the second one by a different power of t. Take the joint distribution, multiply by t, and now it's converging to another mixture, but now it's a mixture of two measures. The measures, miraculously enough, are actually absolutely continuous. They have a joint density. When you see where this density comes from, it's even more miraculous. So here's the density again. The formula, it's not that simple, so don't worry about it. But it's a mixture density, and this density, when we shift to statistics, is going to be a parametric family in the parameter theta, which is 5 parameters, which is really 4 parameters. Okay? That's the answer. Where did it come from? Well, you can represent that limiting random variable with the mass function Pij. First of all, the mixture gets reflected in a Bernoulli random variable. So either you pick the first pair, 1 plus x1 and y1, or the second pair, x2, 1 plus y2, according to the mixing Bernoulli. And
That's even before the limit.
no, that's the limit. That's Pij. Yeah, we've taken the limit n equals infinity here.
No, but not the limit t infinity.
Right, that's correct.
So can you tell me what sort of where this Bernoulli comes from? What is this morally?
You mean more than this?
Yes. What?
No, I can't.
What does it
No, I
correspond
can't.
to in the network?
I can't. No, I don't know.
Because it looks so simple. It's just a coin flip, right? Either you do this. Or
That's correct. I don't have a good explanation for that. This is one of the queasy feelings I get about my understanding of this. There's another. I'm sure there's another way to do this. You embed it in the right process, and it's a birthing thing, and you get a limit. I'm sure there's a better way to do this, but I don't know how to do it yet. And that goes back to that comment about fragility. You know, if you change the assumptions a little bit, you know, you would have to redo all these calculations, which you really don't want to do.
Gamma was.
Gamma
Yes.
and
Gamma
it was sending it out to a new one instead of into a new one, right?
Was-
These are our alpha
Yeah, I know, but I don't remember what alphabet and gamma
I
was.
think this is your notation.
It
actually.
is. It is. I remember coming up
Okay.
with
So
it.
you remember?
So don't blame me.
Yeah,
For,
gamma is the one where you send something out. Alpha is the one you send something in. Gamma is the one you send something out. Beta is the one that you connect to.
internally, right. All right, just hold that thought. We'll talk at the end. Now, if you go back and look at so there's one surprising thing here I want to point out. If you go back and look at the generating function representations, what you wind up with is you have a family of negative binomial random variables indexed by p, and you have a Pareto random variable z, and what you're looking at is x1, y1. There's one family of negative binomials and then another family of negative binomials, but both of them are built on the z. The point being that the heaviness in the tail seems to be coming from one source, the z, and yet you're winding up with a density. So somehow what appears to be a degeneracy here in that pair, somehow the negative binomials smush out the mass enough that you're actually getting a density. You're not winding up on a curve or a line. That's what I found quite striking about this. And similarly, the second pair in the mixture x2, y2. All right. Now, with this representation, you can prove that you actually have the regular variation because things are fairly explicit here, and that's the approach we took. You can also, again, express this in terms of the Laplace transforms. Okay, so now I'm going to talk about the Tauberian approach, and I'm done because I'll run out of time. It's because of the statistics at the end, so blame the statisticians. There's one thing I want to point out about this. Now, why can't you simply take the mass function and attack it directly? What can go wrong? Supposing you have a, well, here are the issues. Suppose you have a regular, oops, sorry, wrong button. Here we go. Right. Suppose you have a regularly varying measure. So now I'm starting with the measure, and I've told you it's regularly varying. Suppose I tell you in addition that it has either a PDF, a density, or a mass function. So I know the measure is regularly varying. What happens to what is essentially the derivative? The answer is, if you've got some monotonicity in the derivative, you can prove it's regularly varying. Without assumptions, that doesn't even work in one dimension. So going from the measure to the density could be tricky without some sort of assumption. The usual assumption, I mean, this was known, I think, in the 30s. The usual assumption is monotonicity. Now go the other way. Suppose I tell you the density or the PD or the PMF, the mass function, is regularly varying. You should be wondering, what do I mean by that? Because I haven't defined it yet. But supposing I tell you the density or the mass function is regularly varying, is the measure regularly varying? That does work in one dimension. It's called Karamata's theorem, or it's one of Karamata's theorems. Doesn't necessarily work in more than one dimension. That's the problem. Things can be too erratic as you move from ray to ray, at least in the standard case. That's the 5-second explanation. So here's the definition that people use, and I think it's the sensible one. Suppose I have an array f on the integer lattice, so fij, as in the case here. I'll define regular variation to be the following. Take two real numbers, x and y, blow them up by scaling functions b1 and b2, then make sure that the product is on the lattice by taking integer part, and then divide by some regularly varying function, and in the limit there should be a non-zero function lambda xy. That would be your definition. So can I prove this for the I and the O, for the Pij? And the answer is yes, you can. Will that imply that the corresponding measure is regularly varying? And the answer is it does, but you need a condition in general which the Pij's can be proven to satisfy. So a typical result in this line is, supposing you have a function on the lattice, uij, and you assume it's regularly varying, and it satisfies something extra, then if the uij is a probability mass function, the measure corresponding to uij will be regularly varying. The easiest example of an extra condition that I referred to up here is something like eventual decreasing. If you're thinking about this being a probability, so it has to go to 0 as you near an infinity. So that would be one way to handle this, that it's eventually decreasing. But the other way is some sort of uniformity condition. And that can be more flexible than this monotonicity. We could not prove that the Pij's were eventually decreasing in both I and j, but we could prove the uniformity condition that we used, which is a little, I mean, it's a kind of, you take a unit sphere and you distort it because of the lack of indices being the same in two directions. And you need uniform convergence on this distorted unit sphere. You can prove that. When you finish, let's see, where is it? Here it is. When you finish, this is now the Pij. So what have I done? Pij, instead of I have x times n to the c1. Remember, that was related to the tail index iota in. NC2Y, you divide by the right thing and you get this limit. And this limit is the density that you had when I said those measures were absolutely continuous. All right, so you can kind of close the loop here and come around at it in all different directions. But generally, we're giving this model a rest. So then you think about fitting this. What would happen if you try and fit it? Your first thought is, what could possibly go wrong? I mean, it's 5 parameters, right? But try and fit a 5-parameter family when you've got millions of data points. So we were not expecting this to work. Let me put it that way. So here are some issues and thoughts that we had as we went along through the analyses. Do you actually trust this model enough that you would try and fit something to it? Which is an interesting question. The alternative might be, don't trust the model so much, but maybe do asymptotic estimation. I could at least, get the tail indices. Why would you consider asymptotic methods? As well as anybody, I know that sometimes these tail methods just are crappy. The true answer is 1.2 and the plot tells you it's 7. It's easy to prove these things, to fool these diagnostics. But the point here is that if you've got model error, the asymptotic methods could be more robust for certain estimation issues. So I didn't dismiss these out of hand. But if the model is accurate, asymptotics is going to do poorly. You're much better off with maximum likelihood. When is the model accurate? If you simulate it. That's about the only way I could guarantee that the model would be accurate. That sounds comical, but I think it's true. Now, there's another statistical issue here, especially if you're thinking in terms of asymptotics. We took a double limit. We let n go to infinity so that the empirical fraction of nodes within degree I and out degree j converged to Pij. And then the regular variation definition really requires I and j to go to infinity in a controlled way, through those scaling functions. So we got this double limit. So there's 2 levels of what I think of as pretend. 2 levels of pretend. First, we pretend, and the people who do peaks over threshold, they use peaks over threshold, whereas I use pretend. But they pretend n equals infinity, so that this empirical fraction is equal to Pij. And then the other level of pretend is that the Pij is represented by the limiting density. Now, somehow you got to do your estimation if you're doing the asymptotics based on something in the data, which is not going to have either n equals infinity or the I and j going to infinity. So there's going to be issues, shall we say. The asymptotics philosophy can be implemented. It doesn't do too badly. We estimated the iota in and iota out using what's called Closet's, sometimes called Closet's method. This is something that's almost the gold standard in computer science and virtually unknown in the statistics bubble, in my experience. So it's basically a minimum distance method for picking thresholds. Usually, you're not sure that you're not sure which of the data pertain to the tail, so you threshold somehow, or you make a plot or something. But this takes care of those issues, and it works reasonably well if the data really is Pareto. Now, a little quibble here, I'll point out. All these methods are really designed for IID data, replicated data, and that's exactly what you don't have here. So, so far we've avoided this issue when we did the asymptotics, but it's going to come back and haunt us, I'm sure. And I'd like to think about this theoretically, just what happens to some of these tail estimators. All right, next issue. So asymptotics versus MLE, that was the first issue. Next issue is what data is really available. Now, sometimes you have the full history of the growth of the network. Now, I'm thinking in terms of social networks here. When we first got this grant, the Army said to us, it's an Army grant. When we first got this grant, the Army said to us, we are very interested in social networks. Imagine that with a, never mind. Wasn't Trump. This is pre-Trump. Don't even go there. All right. Sometimes you do have the full history. There's a lot of data sets on these websites. SNAP, it's a Stanford archive, and Connect is a German archive. Some of the data, it's listed as edges along with a timestamp. I'm not 100% sure that I trust these timestamps, but it appears that you can order the data in terms of edge creation. So we took advantage of that, and we made a full maximum likelihood implementation, and it worked quite well. Now this is, these correspond to, let's see, alpha, beta. We don't need gamma because it's 1 minus alpha plus beta, delta in and delta out. Now, what we did was we simulated 5,000 data sets with a particular set of parameters. For each data set, we created the maximum likelihood estimate. And then we standardized them. And what you're supposed to see here is data which really looks normal 0, 1. What you don't see is a red line, which is the diagonal at the 45 degrees. And there's a second line, which is the QQ, it's R's version QQ line. It's the thing they put through the 25 and 75th percentile. But the estimates really do look normal. We have a couple of theoretical papers where we've looked into the asymptotic normality based on the Martingale central limit theorem. These things are theoretically supposed to be asymptotically normal. The sufficient statistics here, or what's approximately sufficient, they're not quite the statistics we looked at here, but it's close. But there wasn't any real doubt in our mind we should see normality. All right, so if you have the full timestamps, things work pretty well. What if you don't? Supposing you just have a snapshot, there's a kind of approximate maximum likelihood you can work out. The estimators are still consistent and asymptotically normal, but you're taking a hit in terms of efficiency. The asymptotic variance, or the variance of the estimator, is going to be bigger than in the previous case. So the red line now is the 45-degree line. So you can see the variability is tilted, and it doesn't work quite as well, but they still look very normal. All right, now, other issues. I'm going to give you, if I don't run out of time, a real data set, and some weird things were happening with the real data, which is not a surprise, except for naive people like me. But you can have bots and network administrators. What do? They screw up your model by blasting out to the whole network. The network is going down at 3 a.m. Not exactly what you want in a social network, right? So we found we had to clean the data to have any hope of fitting. The other issue is, do you have kind of stationarity, or should you be looking for change points in the parameters? And there's some virtue in looking, okay, there's some virtue of looking for change points. Third point is there's a particular form of preferential attachment that I've assumed here. There are other forms of preferential attachment which might be multiplicative or powers. I have no idea how to sort through the alternatives. And then generally, if you want to fit the real data, you've got to do some mud wrestling. You're going to have to clean the data, get rid of those bots. Sorry. the issue is, do you really expect this low parameter model to fit? There could be more scenarios. The real data has people arriving in pairs already joined to the network. So it would correspond to 2 nodes arriving simultaneously with an edge. And some nodes seem to arrive, these are the self-involved people, they arrive with a self-loop. So we looked at something off Connect, which was Dutch Wikipedia. It seemed to work. And the nodes represent the users, the edges means that I write a comment on your page. There's quite a few data sets which seem to be like that. The group broadcasts exist and must be cleaned out of there. We added 2 scenarios which corresponded to the data. The 4th scenario was where 2 nodes arrive simultaneously joined, and the 5th one where you have the self-loop. So now instead of the 3 alpha, beta, gamma, we have 5, where we really have 4 because they add up to 1. So here's the result of the fit. So this is after you clean the data. You get rid of the bots and the administrator communications. This one is for the delta out. This one is for delta in. And delta out, so what we did is we fit the model, and then we simulated it 20 times. And what you're seeing in green is the frequency distribution for these 20 simulations. And it kind of performs a little confidence region. And if the red sits nicely in it, you feel a little better about your fit. Works for delta in, not so great for delta out. The other issue was change points. Now, before cleaning the data, this is what the black one is delta in. So what we did is we took the range of the data over time, split it into 20 subintervals. There was no particular scientific reason for choosing 20, so don't ask. Work in progress. So you see these big spikes. It tells you, the model is really doing badly there because you think you ought to see something which is fairly constant. Once you clean the data, things don't look so bad by getting rid of the users that I think we're sending out to more than 40 at a time, 40 correspondents at a time. So this is the delta in, delta out after cleaning. These are the beta and gamma, and these are the other parameters. It looks better. Okay, so I think probably I've tested the patience of my chairman, so I will stop. Thank you very much.
Okay, time for 1 or 2 questions.
So when you fit the maximum likelihood estimators, is it before estimating tail parameters, or are you doing pixel threshold and then after that there are?
No, the maximum likelihood does not worry about the tail parameters. It takes those 5 parameters and just estimates them, and then you get your tail parameter estimates from the maximum likelihood because you have a formula which says iota in is some function of all those parameters which you just estimated. So your maximum likelihood estimate of the tail parameters is the function of the 5 parameters, which are really 4.
Okay. So really no thresholding or anything?
No.
The whole data
No.
set.
Now, of course, the Achilles heel, though, is you got to really believe the model.
I was wondering, can you say anything about correlation between in and out degree? From the construction, I would have guessed that they were independent, but I guess
No, they're not.
But can
No.
you say are they positively correlated or negatively correlated?
I spent 4 years trying to get the other people on this grant not to use the word correlation.
Okay. Dependence then of some kind.
No, I don't think there's much you can say. I mean, sometimes, if this limit measure is concentrated on a narrow region, that tells you something about the dependent structure. But in this case, you've got a density and it's smeared all over the different directions, so I don't think it's very, and it will depend on the parameters for sure. So I don't think it's very easy to make a general statement. I could try and compute it. I've never done it.
So I think there's maybe one
But they're not independent. And in fact, what was surprising, what was surprising is they were both dependent on the same z. You know, they were kind of a mixture of this z variable.
I guess empirical ones, they are positively correlated.
I guess, yeah.
Okay, last question in the back.
I was going to ask whether, so if I remember correctly, Jennifer and Christian studied the Benjamini-Schramm limit of PA, right? With Berger?
Yeah, that was an entirely different.
No, but he's wondering whether that limit exists here.
Well, that's a good question too. But does that limit study bear at all on these questions you're asking?
On
And
this one here, no.
no. Okay.
But I think it's a good question.
Yeah. Okay.
The one you didn't ask. Yeah.
So
but
what
anyway,
you actually are-
What people frequently overlook with this is it's really just about the distribution. It's not saying much about how the process is behaving. It's all where the mass is going.
Okay, I think this is a good point to stop. Let's thank Sidney again.